One of the most important tools we have in the study of statics and really all of solid mechanics is the free body diagram. So let's take a little time here to go back and hit some core ideas in the free body diagram, what it means and what it doesn't mean. Right? The basic idea, and let's zoom in just a little bit here, is that a free body diagram is a drawing that represents a body that has been freed from all restraints. And you can think about that meaning that the body, say this prybar here, once it's been taken out of its original context, is like a satellite. Now it's different than a satellite that orbits around some other planetary object in that it actually did have some constraints here. Right? And those constraints in this case were specifically, say down here where this rock B is located, where a displacement of some sort is prevented, or a displacement down here at the rock C. Again, it's some sort of displacement or now remember, displacement doesn't mean translation. It could mean a rotation too. So translation or rotation are being prevented. And in order to prevent those, you have to have a set of forces to prevent that. So when you're removing these things, freeing the body that's left, we have to come back, okay, we've cut away the rock at C, that point of contact, we've cut away the rock B, and that at its point of contact, and we have to represent the forces that that object that was removed could have imparted. Now, this is also true of this person up here pulling. Now, in this case, where the condition of the analysis was that this person is pulling with 225 newtons, and what's the free body diagram that goes along with that? So we're directly representing then on this prybar that the action, the force creating all the action, the applied force, is the 225 newtons, and it's horizontal. Right? So if we're in 2D, then the question really becomes, in a very general way, there are only three sets of things that could possibly be at that point of contact. Potentially a force in the X direction, a force in the Y direction, and some sort of rotational resistance. Note, all three are associated with that right-hand coordinate system, and where we look at translation in one direction, translation in the other direction, a perpendicular direction, and then rotation that could happen essentially about that third axis. Those two translations do not have to be horizontal and vertical. They could be rotated. They are usually taken as 90 degree to each other. They don't actually have to be. There's an infinite number of ways to represent this. Now, it's convenient to always use 90 degrees because that creates an independence between the two. Right? That Fy has no projection onto the x-axis, and the Fx has no projection onto the y-axis. In that sense, they're independent of each other. And if I know what a force is in the x direction and in the y direction, I can resolve these two to some other direction. In certain instances, they must resolve. In others, they are totally independent of each other. So a key question to me, at any rate, when I just make general free body diagrams, is to always ask the question, what displacements are restrained? If I can answer that, then I don't have to go look up in a table somewhere in some set of symbols to figure out what's going on. All right, so let's go back now to this specific situation. We have this prybar, a rock down here at B, another rock here at C. We're tugging on the prybar. Physical reality is that we set this up this way to try to dislodge and move this rock down here. That point B, that rock becomes our leverage point. Right? That's what's really going on. Now, the problem statement says we've got the small ledge on a rock at C also supports a vertical force reaction of some sort. We are to neglect friction at B, and there's also this notion that, hey, there's this mass of the prybar that we got to deal with as well. Right? So we have an applied force of 225 newtons. That's horizontal. That's been given to us. We're told that we do have a uniform bar, which means, hey, its center of mass is going to be at its mid-length, right, at its midpoint. So we can go figure out what this length is, and we can then come in at its midpoint. By scale, that's 2.5 inches, so that would be at 1.25 inches down on the scale. From the standpoint of the dimensions that we've been provided, the prybar in its vertical projection is 1.7 meters long, so 1.7 meters long, so half of that height would be where it's located from that standpoint. And so that would be half of 1.7, that would be 0.85 meters, top and bottom. That would be the location of the center of mass. It becomes a force when we then include the acceleration of gravity. Right? And so that would be 18 kilograms times 9.81 meters per second squared. At least you might use 9.806 if you wanted slightly greater precision. In engineering work, for much of it, we would just use 3 digits of accuracy. Right? So that these now become the applied forces. The 225 externally applied force, the weight acting effectively at the center of mass. It's really distributed along the whole length, but it effectively, from a statics perspective, is going to act at the center of mass as though it were a concentrated force. That's called a body force. And now we got to deal with what we've cut away. Right? Now, at B, they say we neglect the friction at B. Now, if I didn't neglect the friction at B, I would still probably end up with only one force here, and that's because I look at that and it's coming to a point, and there's not a lot that can happen from a sideways kind of perspective here. Yeah, alright, let's not worry about that subtlety just yet. We are told to neglect the friction at B. Now, when you think about removing something and you ask that question, what displacements are possibly restrained? Well, for sure, we've got restraint at 20 degrees from the horizontal in terms of displacements right here at point B. That's perpendicular to the surface. So there's your point B right there, and perpendicular to that, we are absolutely providing some resistance from the soil. I don't even have to worry about whether or not that soil is infinitely stiff or if it's flexible. Don't know, don't care. There is a force, a normal force, here at B. And then the only other possible one, again, 2 orthogonal forces, right? So the only other possible force would be one that is parallel, but we're told to neglect friction at B. So that possible frictional force at B is going to be 0. We don't even need to show it, but I do here just to emphasize. In any situation there, we've only got 2 possible forces to have to represent, and we're told the parallel one, the frictional one, is going to be 0. We only have the normal. Now then you say, okay, so we're not restricting displacement along the shaft. We are restricting displacement at point B perpendicular to the shaft or the prybar. What about rotation? That's the critical part about this coming to a point. There's nothing here that prevents rotation here. So there's going to be no moment showing. I'll go ahead and show a dashed line. It's 0 also. We only have one and one unknown here. This is a lot like a roller on an inclined plane, same kind of thing. Now there's not probably a hold down force like a roller would provide, because I could take this prybar and rotate it out this way, and there would be no restraint from that offered by B, unless somehow I came in and bonded with epoxy the prybar to the rock. I don't know why I would ever do that. Probably wouldn't. Right? So we have one and only one force pushing back on the prybar at B. Now at C, we're told there is a possible vertical reaction here, and there's got to be some sort of general sense of you're doing this whole thing, you're going to want to try to, as this bar rotates, try to push C to the side, so there will be resistance there as well. So we get both of these involved. And you might rotate these so that they are normal to the bar and parallel to the bar. You could do it that way. It's not usually convenient to do it that way, and particularly not convenient here, because we've got the 225 acting to the right. We've got the normal force at B having an X component globally going back to the left. I'm not much sure what I said about 225 acting to the right. We got something going to the left, and because I've done a lot of problems here, that's probably going to be a pretty large force and a pretty big X component. I'm going to guess, oh wait a minute, I don't have to guess. Hey, this thing wants to rotate about point B. It's trying to shove the rock to the left, that means the rock is probably pushing back on the prybar. It's hard to believe that it would be anything but that. And that means that, hey, the x component of NB, when we do equilibrium sum of forces of the x, it's going to be the sum of Cx and 225. It's going to balance out that way, right? And then we're capable of having a vertical reaction at C. There's a little ledge. I don't know if the rock, if when we try to crank this thing over, are we going to lift up on the rock? My intuition says actually probably yes. So I'm going to guess that it's going downwards, but without numbers here, I don't know what's going to really happen. Right? We got the weight vector going down. We have a little bit of n sub b that its y component that is going up. What's going to be the balance between those two? Will we really have a net going downwards? Interesting question. We need to do some calculations to try to figure that out. We could do it because we got 1, 2, 3 unknowns. We have a free body diagram that is not concurrent, so therefore we have 3 equations of equilibrium that we could represent as sum of forces of the x, sum of forces of the y, and sum of the moments if we wanted to. Or we could sum moments about b. That would give us a relationship between Cx, Cy, and the weight and the 225. That's one equation, 2 unknowns. I could sum moments about C, and I'd have NB in terms of moment effects of W and the 225. I like that. One equation, one unknown. I can find out what n sub b is. And then we've got, well, another sum of moments if we wanted to. We could sum moments up here where the line of action of 225 and Cy go away. We'd get a relationship between Cx and NB. There's a lot of ways we could work with having 3 equilibrium equations and 3 unknowns. We can write an infinite number of equilibrium equations, but only 3 are independent, and so we can only solve at most for 3 unknowns. Right, now that's getting into the equilibrium side. Let's go back. The whole point of this was to get in more detail about free body diagrams and this key idea of, well, what displacements are restrained in some sense. They don't have to be 0, but what are they? What are the restraints at C that rock is going to restrain some of the displacement or translation in the x direction? We're told that it can also do something with the y, because we're told that there's a capability of a vertical force reaction there. At B, because we're neglecting friction, there's no restraint parallel to the surface, but there certainly is perpendicular. And then we have these 2 applied forces in the system. There you go. There is a complete free body diagram, and one that is statically determinate. We can determine the 3 unknowns using the 3 available equations of equilibrium.